So welcome everyone to the ITMP seminar. And today we have Francois Rondeau from University of Cyprus. Sorry, I confused your affiliation. And he's going to talk about G-2 from Intersecting D-branes. So please, you're welcome to start.
Okay, so thank you very much. Can you, yes, my microphone is on. So thank you very much for the invitation. So I'm going to present part of our recent work, which try to address the issue in the anomalous magnetic moment of the muon in the framework of intersecting D-branes, a work which has been carried out in collaboration with Pascal Anastasopoulos, Elias Niederwieser from Vienna University, and Ignatios Antoniadis from LPTHE in Paris. The plan for my talk is the following. So I will first remind the basic aspect of the anomalous magnetic moment of the muon, as well as the physics of intersecting D-branes. And I will then present two proposals which try to solve the discrepancy in the G-2 of the muon. The first one using extra U1 gauge boson, which has the property to be leptophilic. And the second proposal using light stringy states of the Higgs field. So let me start by reminding the very basic aspects about the magnetic moment of the muon. So what we call the Landé G factor, G is a proportionality constant between the magnetic moment of an elementary particle, mu, and its spin S. So at tree level, Dirac equations predict this quantity to be strictly equals to 2. And then we can compute the quantum corrections to this value. And it turns out that the quantum corrections can be extracted from the following diagram, which is the interaction between the lepton and the photon, which can be parameterized in the following way at all orders of perturbation theory, where F1 and F2 are two functions called form factor, and which turns out to encode both the electric charge and the anomalous magnetic moment of the particle. So F1 gives the electric charge of the particle under consideration, and F2 gives the deviation of G from 2, from its tree level value 2. So at tree level, F2 equals 0, and then we can ask how can we compute the quantum corrections to F2. So if I want to compute the one-loop correction to the anomalous magnetic moment of the muon, I have to compute the one-loop correction to F2, which comes from this diagram, which is the vertex correction to the lepton-photon vertex. So I can compute this diagram using the Feynman rules, and I get the following expression, where small m is the mass of the lepton, and capital N is the mass of the massive gauge boson, which is exchanged here in the loop. So in the most general case, we can have massive gauge boson exchanged in the loop with mass capital M. And so I get here the one loop correction to the G-2, which I call small a. So if you take capital M equals 0, you find the standard result of QED, where we have a photon which is exchanged in the loop, which is a result originally found by Schwinger in 1948. So you can do similar computations, so in the QED sector of the standard model, in the electroweak sector, in the QCD sector. You put everything together and you find the theoretical prediction to the anomalous magnetic moment, which is the quantity I call A mu standard model. And then people have measured this quantity experimentally at Brookhaven National Lab and at Fermilab more recently. And they find a quantity A mu experimental, which differs from the theoretical prediction by a significant amount of 10 to the minus 9, which corresponds to a standard deviation of 4.7 sigma. And so there have been many proposals in the past months and years in order to explain this discrepancy using new physics. And so the goal of my talk is to propose some solution to explain this discrepancy in the framework of intersecting D-brane physics in string theory. So what do we mean by intersecting D-brane physics? So let's start by considering a single DP brane with an open string which is attached to it. So we know that the massless spectrum contains a U1 vector, and the number of scalars we have. So we have one scalar for each direction transverse to the brane, and a bunch of non-chiral fermions so that the spectrum is supersymmetric. That's for a single DP brane. Then we can consider to have n parallel DP branes. So you take a stack of n coincident parallel DP branes with an open string which is attached to this stack. So the first n of the string has n possibilities to sit. The second n has also n possibilities to sit. And so we end with n square distinct copies of the spectrum. And so the spectrum is n square copies of the spectrum for a single U1 brane. Then we can consider the case where we have branes which intersect, so which are not parallel, but which intersect with a given angle, and an open string which stretches between these two branes. And in this case, the spectrum contains so complex scalars, as well as massless four-dimensional chiral fermions. And so you see that with this construction, we can get very easily non-abelian gauge symmetries, as well as chiral matter, which are the two main ingredients on which the standard model physics, the standard model of particle physics is built. And so there has been many proposals in the past to try to obtain the standard model of particle physics from string theory using this framework of intersecting D-brane. So let me elaborate a bit more on this idea. So by considering first a stack of n parallel D-branes. So as I said, if I consider an open string which is tied to a stack of n parallel D-branes, I get a gauge group which is un, which is equal to sun times u1. And so from this perspective, we can easily reproduce the gauge sector of the standard model. So let's consider, for instance, a stack of 3 parallel D-branes, which are represented schematically here. And then an open string which is attached to it will reproduce the gluon, so the SU3 gauge boson of the standard model, plus an additional abelian gauge vector. So the idea to keep in mind here is that the gauge boson live in the world volume of parallel D-branes. So you can play with it and you can reproduce the full gauge sector of the standard model. So let's consider, for instance, a simple model with 4 stacks of brane. So I have one stack of 3 parallel D-branes, the green stack. I have one stack of 2 parallel branes, the blue one. And I have 2 stacks of 1 single brane, the yellow and the red one. So an open string attached to the green one will give rise to the SU3 gauge boson. An open string attached to the blue one will give rise to the SU2 gauge boson. And then we have 4 remaining abelian factors associated to each stack of brane. So that in the most general case, the hypercharge will be a linear combination of these 4 abelian factors. Linear combination, which is written here. And so we end with 3 extra abelian gauge fields, which turns out to be anomalous and to gain some mass through the Green-Schwarz anomaly cancellation mechanism. So we have one massless U1, which is a hypercharge, and all the remaining extra gauge fields, extra abelian gauge fields, are massive. So in the first part of this talk, I will consider the contribution to the muon G-2, which comes from the Kaluza-Klein modes of an extra U1 gauge boson, which we'll consider to be leptophilic. I will explain why in the following. That will be the first part of this presentation.
Quick question. So just
Yes.
to put it on in simple words. So what you're trying to do, you're trying to suggest some extension of standard model, which is motivated by this D-brane construction, right? So
Yes.
That's all. So you're not really going to consider any stringy physics or anything like that. So it's just massless light modes which come out of this D-brane construction.
Yes, that's a bottom-up approach. So it's an extension of the standard model with extra gauge bosons, which can accommodate the muon G-2.
Okay, so it's important that this is spin 1 particles, right?
For this case, yes.
Okay.
For this first part. In the second part of the talk, I will consider scalar excitations.
Okay. Thank you.
So that will be the first part of this talk. So let me continue to this framework of intersecting D-brane. So we have seen how can we build, how can we reproduce the gauge sector of the standard model. And so what about the matter sector of the standard model? So as I said, if I consider open strings stretched between two stacks of D-branes, so for instance, I consider a stack of M D-branes and a stack of N D-branes, and I consider an open string which is stretched between them. Then it transforms in the bifundamental representation N, N bar of the gauge group UN times UN. And so from this perspective, we can reproduce the standard model spectrum, the standard model matter spectrum. So let's consider a stack of 3 and a stack of 2 branes, again, these green and these blue stacks. An open string which is stretched between them transformed in the 3,2 representation, which is precisely a left-handed quark doublet, which is the left-handed quark doublet, QN, of the standard model. So again, we can play with this model of 4 stacks of brane and reproduce all the matter spectrum of the standard model in this configuration. So we have seen the left-handed quark doublet. We have the right-handed quark singlets, which are singlets under SU2, so they must not be tied to the blue stacks of brane. They must have so one end on the green stack, so that they belong to the fundamental of SU3. And they must have their second end on a single U1 brane, so the green, the red, and the yellow. Then we have the Higgs doublet and the left-handed lepton doublets, which are doublets of SU2, so they must have one end on the blue stack of branes, no end on the green stack, and so their second end must be attached to a single U1 brane, the yellow and the red. And then we have the right-handed electron, and we can introduce as well the right-handed neutrinos, which are both singlets under SU3 and SU2, and so they must have both ends, tied to a single U1 brane. So the main idea to keep in mind here is that the standard model particles, matter particles, live at intersections of D-branes. So they live at intersections of D-branes, but the point to notice is that they are not alone in this intersection. So they are actually the lightest modes, the massless modes, among an infinite tower of states which live in the intersection. So at each intersection, we have these massless modes, which are followed by an infinite number of massive copies, which becomes more and more massive as we go up in the tower. So we have an infinite number of copies of the standard model at each intersection. And so in the second part of this talk, I will be interested in the contribution to the G-2, which come from such excitations for the Higgs. So I have depicted here. So what I call H is a massless, is a zero mode for the Higgs, and H tilde, H double tilde are the excitations which live in this intersection. And I will study the contribution to the G-2, which comes from these excitations. So last slide to conclude this introduction. So I will be interested in the excitation of a scalar. So we will need the Yukawa coupling of these scalars. So just to schematically depict how does the procedure work. So we have this Higgs, which I call capital H, the excitation H tilde, H double tilde, and the point to notice that the Yukawa couplings between these Higgs and the fermions can be fully expressed in terms of the geometric parameters of this internal manifold where the branes intersect. So I will not go into the details of this formula, but just to show that these Yukawas can be fully expressed in terms of the angles. So theta H, theta Q, and theta U are the intersection angles where these fields live. And capital A is the area of the triangle, which is the green triangle, where these fields live. So basically, we can relate the geometric parameters of the internal manifold with the Yukawa. and the Yukawas are related to the G-2 of the muon. So ultimately, we will be able to relate the G-2 discrepancy to some geometric parameters in the internal manifold. So that's the end of the introduction. So if you have questions, please go ahead. Otherwise, I can start on the first part of the talk.
Just like a naive question.
Yes.
So as I understand, you have like many extra dimensions, and the pattern of intersection can be like more complicated. So you are drawing everything is like on the plane, right? And like there is a single angle.
Yes. So that's that schematic. You mean what do I depict here by this?
Yeah. Well, I mean, let's say in 3D, if you have two lines, they may not intersect. Right?
So the branes intersect in the 6-dimensional internal manifold, compact manifold.
Mm-hmm.
So I will, yes.
Yeah, and there is only like a single angle that parameterizes like the way how they intersect, right?
Sorry?
And there is only a single angle which parameterizes the way how they.
There will be several angles. I will show a picture a bit later. So there are several angles for each tori. So we have a 6-dimensional internal space, which can be factorized in a T6, which can be factorized in 3 2 tori. And so we have intersection angle of in each of these 3 tori. So we have several intersection angles. I will come back to this point a bit later.
Mm-hmm. Okay, thank you.
So let's start with the first part. So in the first part of this work, we have been interested into the contribution to the muon J-2 coming from an extra U1 gauge boson, which has a property to be leptophilic. So this is a work carried out in collaboration with Luis Sancordotti, Ignatius Antoniadis, Xing Huang, Dieter Lust, and Thomas Taylor, as well as in a second publication with Ignatius Antoniadis. So this work is motivated by the following observation, which has been done in this publication here, where the authors have noticed that the muon G-2 discrepancy can be accommodated from the following proposal. So let's assume that we gauge the lepton number U1 symmetry of the standard model, and we assume the associated gauge boson to propagate along at least one extra dimension. So in this case, what do we have for the spectrum? So we have the zero mode. It's a zero mode of an extra U1 gauge boson. So as I said above, it's anomalous, and it gets a mass through the Green-Schwarz anomaly cancellation mechanism. So it gets a mass of order of the string scale. So it's quite EV. And it's too EV to accommodate the G-2. So it just gives a negligible contribution. And I will not consider the zero mode anymore. But then we have the Kaluza-Klein mode. And the Kaluza-Klein mode, so they couple only to leptons at tree level, because we have a leptophilic, we consider a leptophilic U1 gauge boson. And because they couple only to leptons, they completely evade the LHC bonds. They don't couple to quark. They evade the LHC bonds, and they can be sufficiently light to give significant contribution to the G-2. So we have a quite peculiar spectrum with a zero mode, which has a mass at the string scale, and some Kaluza-Klein modes which can be lighter than this zero mode. And we will be interested in the contribution to the G-2 coming from these light Kaluza-Klein modes. So in this case, since it couples only to lepton and not to quarks, the experimental bond on this extra Kaluza-Klein modes comes from the LEP data and comes from the following interaction diagram. So I call Z prime this extra gauge boson, which couples only to lepton. And so we have a bound on the propagator of this extra gauge boson. Since I consider all the Kaluza-Klein modes, I have to sum over all the KK modes. And so we have a bound which is given by this quantity. So let's consider first that the mass of the compactification scale, so the mass of the first Kaluza-Klein mode, is much bigger than the typical LEP energy, which is at 200 GeV. So this LEP constraint simplifies into the following form. On one hand. On the other hand, I can take the expression, the integral expression giving the G-2 discrepancy, giving the contribution to the G-2 that I wrote above in the introduction. I use this assumption that m is much bigger than square root of s, and I give this expression for the G-2 contribution. So I can combine these two relations, and I find an upper bound on the contribution coming from the Kaluza-Klein modes to the G-2, which is 10 to the minus 11, to be compared to the discrepancy, which is at 10 to the minus 9. So that's too small to contribute to explain the discrepancy. And so we cannot explain the discrepancy with such a compactification scale. So the conclusion is that we need at least one or few Kaluza-Klein states whose mass is much smaller than 200 GeV. So let's elaborate a bit more on this case. So first, let me remind that we have a gauge boson which propagates along some extra dimensions. So its four-dimensional effective gauge coupling is suppressed by the volume V of these extra dimensions, which in the case of one extra dimension gives the following relation, which involves the string coupling GS, the compactification scale N, and the string scale MS. So as I said, now I want to consider M to be much smaller than square root of S and bigger than the mass of the muon. We take the integral expression for the contribution to the G-2, we simplify it in this limit, and we get the following relation, again in terms of the compactification scale and the string scale. And now we can ask this contribution to fully bridge the gap, to fully bridge the discrepancy. So capital delta A mu is the observed discrepancy in the G-2 of the muon, 10 to the minus 9. And that small delta A mu is the contribution to the G-2 coming from the Kaluza-Klein modes. And so if we impose the KK modes to fully contribute to the discrepancy, we get a relation between the compactification scale, the string scale, and the string coupling. So we have a lower bound on the string scale at 10 TeV. GS must be smaller to 4 pi to stay in the perturbative regime. And so we get an highest compactification scale M of order 60 GeV. So indeed, we can check that this value indeed satisfies this relation. So we are below the LEP energy. And we can plug these values into the LEP bound and see that the LEP bound is indeed satisfied. So we have a region of the parameter space, which is compatible with the experimental bounds, where the contribution to such Kaluza-Klein modes can accommodate the G-2 discrepancy. So just to notice that we have also found other regions of the parameter space. So for instance, if I take M to be of order of mu, or even F to be much smaller than mu, there are other regions of the parameter space where this bound is satisfied and where the Kaluza-Klein modes can provide interesting contribution to the G-2. So we have several regions of the parameter space where these KK modes make the job. So we are using extra U1 gauge boson and extra dimensions, which are ingredients ubiquitous in an intersecting D-brane model. So it's natural to try to embed this proposal into a consistent intersecting D-brane model. So to realize, what we want to do now is to realize this proposal into some intersecting D-brane models. So to this purpose, let me first consider a toy model with 3 stacks of D-branes, which gives rise to a gauge group UN1 times UN2 times UN3. So you have one stack of N1 parallel D-branes, one stack of N2 parallel D-branes, and one stack of N3 parallel D-branes. Then what I call the D-brane basis is a basis of the abelian factors associated to each stacks of brane, B1, B2, B3. Then the hypercharge in general will be a linear combination of these B fields, of these abelian fields. And the combination orthogonal to the hypercharge are anomalous, and I call them A and A prime. And this basis of Y, A, and A prime is what I call the hypercharge basis. So the U1 charges of the hypercharge basis will be linear combination of the U1 charges of the D-brane basis, Qi. And what we want to do, we would like to relate the gauge bosons in the D-brane basis from the gauge bosons in the hypercharge basis. So to do this, we write the covariant derivative in both bases, in the D-brane and in the hypercharge basis. We replace the U1 charges by their linear combination here. We identify the different term, and we can write the rotation matrix, which relates the hypercharge basis to the D-brane basis here. That's a rotation matrix, so we should impose orthogonality condition on it, which gives the following relation between the gauge coupling of the different vectors. And so the point to note here is that if the hypercharge is a linear combination of the different vectors in the D-brane basis, then it's the inverse of the gauge coupling of the hypercharge, which will be a linear combination of the inverses of the gauge coupling of the different U1 in the D-brane basis. And so in particular, if you have a U1 factor in the D-brane basis, which is extending in the bulk, then its four-dimensional gauge coupling will be suppressed by the volume of the extra dimension, which leads in the large volume limit to an ultra-weak gauge coupling for the hypercharge. So you just plug this relation into this relation here. And in the large volume limit, you see that you get an ultra-weak gauge coupling, which is not acceptable phenomenologically. And so the conclusion of this analysis is that any U1 factor which is extending in the bulk should not contribute to the hypercharge. So we want to do our D-brane construction. So we have two main requirements for this construction. The first one is that U1L, so U1L is a single brane which gives rise to the leptophilic gauge boson. We need to have Kaluza-Klein modes of this gauge boson. So we want this U1L to be extending in the bulk. First requirement. And second requirement, as I explained, because it's extending in the bulk, the U1L should not participate to the hypercharge. And so following these two requirements, we find a minimal configuration which requires at least 5 stacks of D-brane. So that the total gauge group is the following. So we have the non-abelian structure SU3 times SU2. We have 3 abelian factors localized in 4 dimensions, U1 color, U1 weak, and a third U1. And we have 2 U1 extending in the bulk. So we have the U1L, which gives rise to the leptophilic gauge boson, and the 5th U1, which I call U1 prime, both of them being extended in the bulk. So before going further, let me explain what I mean by bulk. So here what is important to notice is that we have an inhomogeneous bulk with 2 inhomogeneous compactification scales. So the first one is the one I call the L bulk. Is a bulk along which the U1L brane extends, whose size is around 100 GeV. And the size is fixed by imposing the condition that the Kaluza-Klein modes accommodate the G-2 discrepancy. Then we work in a low string scale model. So we have a string scale around 10 TeV. And so in order to lower the string scale in this TeV region, we need extra large dimensions where only gravity propagates, which I call the gravitational bulk. So that's the framework of large extra dimension introduced years ago by Arkani Ahmed, Antoniadis, Dimopoulos, and Valli, where the string scale can be lower in the TeV region using large extra dimensions where only gravity can propagate, which I call gravitational bulk. So we have this inhomogeneous structure for the bulk. The U1L brane extends only along the L bulk, but the 5th U1 prime factor, a priori, can extend also along some extra dimensions of the gravitational bulk. So how does the D-brane construction work? So we have 2 factors two U1 factors extending in the bulk, which should not contribute to the hypercharge. So the hypercharge is the linear combination of the three factors localized in 4 dimensions. So what do we have for the lepton sector? So in the lepton sector, we have the left-handed lepton doublet and the right-handed lepton doublet, which must have opposite lepton number, epsilon L and minus epsilon L, denoted in red here. This QL does not enter the hypercharge. So imposing L and EC to have the correct hypercharge uniquely fixes the constant C1 and C2 in this linear combination. So you just replace the Q3, Q2, and Q1 in this relation by the values for L and EC. You impose L and EC to have the correct hypercharge, and you find uniquely C1 equals 1 and C2 equals -1. So there is no freedom in the leptonic sector, in the lepton sector. Everything is fixed, and the two constants are uniquely fixed. Then we have the quark sector, where we have the quark doublet and the quark singlet. And here we see that there are two possibilities which lead to the correct hypercharge for these particles. So depending on the value of V here, which can be plus or -1, you get two different models with different quantum numbers for the UC and DC quarks. So you get two models. I have schematically depicted one model here. So here is the hypercharge. We have the different the quantum numbers for the standard model spectrum here, with respect to the different non-abelian and abelian factors of the gauge group. And here, so the three vertical branes are the branes which are localized in 4 dimensions. The linear combination, the hypercharge is a linear combination of the abelian factors in these 3 branes. And the 2 horizontal branes are the branes which extend into some extra dimensions. The U1L in the L bulk and the U1 prime in the gravitational bulk. So that's an example of one of the 2 models that we can get. And then we have to do an anomaly analysis of this model. So we have to check which U1s is anomalous or anomaly-free. And so what we find is that there is 2 anomaly-free U1s. So the first one is the hypercharge. The hypercharge should be anomalous. So it should be anomaly-free, sorry. So we have to check this. And the second anomaly-free U1 is a given linear combination. So it's this Q linear combinations, which turns out to be invisible from the standard model particles. So actually, the standard model particles see only one anomaly-free U1, which is the hypercharge as expected. And then there is an important property of the hypercharge to be checked, is that the hypercharge should remain massless. So an important point, the crucial point here to notice is that it's not because we have an anomaly-free U1 in 4D that this U1 is necessarily massless. Why? Because we can have anomalies in 6 dimensions. So we can have an anomalous U1 in 6 dimensions. Then we have a Green-Schwarz anomaly cancellation mechanism which cancels these anomalies in 6D, which gives a mass to the vector. And so from the 4D point of view, we could have a massive vectors, which is anomaly-free. And so we have to impose additional model-dependent constraints to ensure that the hypercharge remains massless in 4D. And so we have checked this in the example of type 2A identifold compactification with D6 branes and O6 plane, and have shown indeed that the massless condition for the hypercharge can be satisfied. So we have a consistent model from a bottom-up approach, from a phenomenological point of view. We have a consistent model able to explain the discrepancy of the G-2 of the mu. So just to conclude this first part, so we can implement other phenomenological application in this model. So we have 2 branes which are extending the bulk and which does not participate to the hypercharge. And so we can use these branes in a very simple way to introduce additional fermions which has vanishing hypercharge. And in particular, we can introduce the right-handed neutrinos or potential dark matter candidate as being Dirac fermion corresponding to open string stretched between these two branes, which does not participate to the hypercharge. So that, and we have shown that we can indeed consider dark matter candidates, which gives the correct dark matter relic density. So that's just a kind of bonus in this model to implement other phenomenological applications. So that concludes the end of the first part. If you have some questions, otherwise I can move to the second part of this talk. Okay, so if there is no questions, I can now move to the second part, which considers the contribution to the muon G-2 coming from light scalar stringy states, a work carried out in collaboration with Pascal Anastasopoulos and Elias Niederwieser from Vienna University. So in this talk, we'll be interested in the contribution to the G-2 coming from scalar fields. So this contribution again comes from the following vertex correction to the lepton photon vertex, where now we have a scalar which is exchanged in the loop here. So you compute this graph and you can extract the contribution to the G-2 coming from the scalar. So here lambda is the Yukawa coupling between the lepton and the scalar. ML is the mass of the lepton and M phi is the mass of the massive scalar exchange in the loop. So you can plug in this relation the mass of the muon, the mass of the standard model Higgs, the Yukawa coupling between the standard model Higgs and the muon, and you find a contribution from the standard model Higgs to be of order 10 to the minus 14, so much smaller than the discrepancy. So that is a well-known result that the standard model Higgs gives a very negligible contribution to the G-2. But what is interesting is when we consider scalar field now which couples only to the muon. And in this case, the experimental bonds are much weaker and we can have much smaller scalar field with a mass as light as 2 times the mass of the muon. So the idea is very similar to what we did in the first part. In the first part, we consider leptophilic gauge boson, which did not couple to quark, and so which evades the LHC bonds. Here, the idea is the same. We consider a scalar field which does not couple to quarks and which does not couple to the electron. So most of the experimental bonds do not apply here, and we can have a quite low scalar field, sufficiently low to give significant contribution to the G-2. And so the question we can ask is then, how can we get such light scalar states in the framework of intersecting D-brane physics? So as I said in the introduction, if I consider an open string which is stretched between 2 stacks of intersecting D-brane, in the intersection, I have the zero mode, which I call psi here, which is followed by an infinite tower of massive states. Sorry. And the mass of these states, or the mass square of these states, are proportional to the string scale square. And the proportionality constant is the angle, theta over pi, the angle of the intersection of the two stacks of branes. And so in the case where you have very, very small angles, then you can get very light states, which is what we call light stringy states. So in our case, we have the bound for the scalar, which is around 2 times the mass of the muon. So we can fix the idea by take a massive scalar of mass 250 MeV. So that will be the first excited state living in this tower of states. We have the lower bound for the string scale, which is at 10 TeV, which yields an upper bound from the intersection angle around 10 to the minus 10. So we have a very, very small angle, which can give rise to such light scalar field, light excitation. So that's for the mass. Then what about the Yukawa coupling of this scalar? So using the formula I wrote above, giving the Yukawa in terms of the mass and the contribution to the G-2, I can plot the Yukawa coupling of the first excited state in terms of the mass of the scalar for different contribution to the G-2. So the blue curve is for if this scalar contributes to the full discrepancy of the G-2, so 10 to the minus 9. The green curve is when the scalar contributes to 1/10 of the full discrepancy, so 10 to the minus 10, and so on for the other curves. And what we would like to do, what we would like to have, is to have a Yukawa for the first excited state to be smaller than the Yukawa of the zero mode, because we have this tower of states, and we would like the Yukawa to decrease as we go up in the tower. And so from this plot, you see that if you impose the excitations to contribute to the full discrepancy, then you get a Yukawa in blue, which is bigger than the Yukawa of the zero mode of the Higgs, of the scalar. And so we want to exclude this possibility. And so instead of considering a full contribution to the G-2, we will assume that the first excitations gives a significant contribution, but which remains smaller than the full discrepancy, 10 to the minus 9. And so typically, we will consider a contribution to be 1/10 of the full discrepancy. So we will assume the first excited state to contribute to 10 to the minus 10. So what is our intersecting D-brane framework? So we have these branes which span the 4-dimensional Minkowski space and which intersect in the internal manifold. So for simplicity, we consider this internal space to be T6, and we assume it to be factorizable into 3 two-torus, T12, T22, and T32. So we have these branes which intersect in these 3 torus, in these 3 internal torus, and we have this tower of states living in each intersection. So maybe that answers the question you asked me at the beginning about these different angles. So indeed, we have intersection angle in each of these torus. And I will call them, as you see, theta 1 AB, theta 2 AB, theta 3 AB, where 1, 2, and 3 denotes the torus we consider. So here we will do 2 more assumptions. The first one is that the lightest excitations of all the standard model particles are the Higgs excitations. So that's a reasonable assumption because we consider light excitation for the Higgs. If we would have other standard model particles with lighter excitations, they would have been observed experimentally. So it's quite reasonable to assume that there is no lighter excitations for the lepton or for the quarks or for other standard model particles. So the Higgs excitations are the lightest ones. And then without loss of generality, we can assume that the lightest excitation live in the first torus. So we will consider that the smallest angle is the theta 1 angle. So AB is the intersection where the scalar field lives, and 1 is the first torus. So I will now consider the excited states, the tower of excited states, living in the AB intersection of the first torus. So here is this first torus, which is schematically depicted in this picture. And again, the idea that I have already introduced in the beginning is that we can express the Yukawa coupling of the first excited mode of the Higgs in terms of the geometric parameters. So lambda mu is the Yukawa coupling of the zero mode of the scalar, and lambda tilde is the Yukawa coupling of the first excited state, which is given in terms of these geometric parameters. So the small a's are the angles normalized by pi. So A1AB, A1BC, and A1CA are the 3 angles in this triangle. And capital A is the area of this small triangle, which is here. So we have these geometric quantities, and an important quantity that we will work on in the following, that we will work with in the following, is this length f. So f is the length of the size of the triangle, which is opposite to the small angle theta 1 AB. So here is theta 1 AB. And the size of the triangle opposite to theta 1 AB is the quantity that I call f, and on which we will put constraints using the G-2 discrepancy. So let me summarize what we have for now. So we have fixed the mass of the scalar to be 250 MeV. We have a low string scale at 10 TeV, which can be realized if we have a very small intersection angle of order 10 to the minus 10. Then I have explained why we consider a contribution to the G-2 discrepancy to be 1/10 of the full discrepancy. So a contribution of order 10 to the minus 10, which gives a Yukawa coupling for the first excited state to be 10 to the minus 4. Then we consider supersymmetric configuration. So we have condition on the intersection angle, which ensures that supersymmetry is locally preserved. And so we have this relation between the different intersection angles. So in terms of, instead of having 3 independent angles, we actually have 2 independent angles. We have already fixed one angle. So at the end, there is just one free angle, which we choose to be the angle A1BC. And so at the end, we get 2 free parameters, the length F that I talked in the previous slide, and one angle A1BC. And so we can express F as a function of A1BC and plot this function for the different parameters that I wrote here for A1BC varying between 0 and 1. So A1BC is an angle normalized by pi, so it varies between 0 and 1. And we have this function F, which is the length in this triangle. And so for this plot, you see that for an angle between 0 and 1, we get a length which is of order 10 to the minus 8 GV minus 1, which is consistent with the bounds on the extra dimension of the size of the extra dimensions, and which gives a lower bound for one size of the first two torus where the tower of states lives. So this F is just a length in this torus. So the size of the torus can be bigger than this F, but it cannot be smaller, of course. So we have a bound for one size of the extra dimension. That's for the contribution of the first excited mode. And then we can consider the contribution of the second excited state, which I called H double tilde. So now its mass square is twice the mass square of the first excited state. And again, we can express the Yukawa coupling of the second excited state in terms of the geometric parameters. So again, we have this function of the angles, A1BC, A1AB, A1CA. Capital A is the area of the triangle, and lambda, which is the Yukawa of the zero mode. And what is interesting to note here is that there are regions where the Yukawa for the second excited mode is bigger than the Yukawa of the first excited mode, which implies that H double tilde will contribute more to the G-2 than H tilde, which again is something that we don't want because we have this tower of states and we want the Yukawas to decrease as we go up in the tower. And we want the contribution of the excited states to become more and more, to become smaller and smaller as we go up in this tower. So to see this effect, we can fix the angle A1BC. Again, we consider an angle, we keep the same value for the angle A1AB, 10 to the minus 10. We have a string scale at 10 TeV, and we can plot the different contributions to the G-2 coming from the first excited state, the second excited state. So the first one is a blue curve. The contribution coming from the second excited state is a green curve. And the red one is the sum of the two. The horizontal blue band being the G-2 discrepancy. And so you see that here, at the end of the plot and at the beginning of the plot, there are regions where the contribution coming from the second X is actually bigger than the contribution coming from the first X. And so to be consistent, we should remain in this region here, where the contribution of the second X is negligible compared to the contribution of the first one. So what we have at the end is that we have an interval for F, which must be bounded by 10 to the minus 12 MeV minus 1 and 10 to the minus 11 MeV minus 1. So we have a region of the parameter space for F, where the contribution to the G-2 is dominated by the first excitation, and then the second excitation gives negligible contribution. So we have this region of the parameter space able to give significant contribution to the G-2 of the muon. So now that we have this, in a similar way as I explained in the first part, we can build the minimal D-brane construction which realize this proposal. So to fix the IDs, I will call HD the Higgs, which has very light excitations, which contribute to the G-2. As I said, these Higgs can be quite light because it couples only to the muon. So in our D-brane construction, we should ensure that there is no three-level coupling between the electron and HD, nor between the quarks and HD. So HD should only couple at three level to the muon. And the second requirement to impose on our construction is that the HD is the only field living in this small intersection. Otherwise, if we have other standard model field living in this intersection, we would have other light excitations for the lepton, for instance, which is phenomenologically excluded. So we need to have HD to be the only field living in this very small intersection angle. And so you can implement these two conditions again, and you find that the minimal configuration which satisfies these 2 points contains 4 stacks of D-branes, which leads to the following gauge group, where now you have 4 abelian factors. So you have different models like this. You have different hypercharge embedding, which satisfies these conditions. And I have depicted here, so schematically, 1 possibility with the following hypercharge, which is a linear combination of 3 among the 4 abelian factors. So the Higgs, which has light excitation, is the blue one, HD, which is depicted here. So what we want, as I said, is that HD should be the only field living in the intersection between the U2 stacks of brane and the U1 prime stacks of brane. So there must be no other open string stretch between these 2 stacks. And the second possibility, the second condition, sorry, is that HD should not couple at 3 level to the quarks or to the nor to the electron, which can be imposed by imposing the following quantum numbers for Q and LE to be +1. So the red quantum numbers are the quantum numbers that need to be chosen, so that HD does not couple at 3 level to Q, does not couple at 3 level to L electron, but couples at 3 level to the muon. And so why do we have this freedom? Because the second abelian factor does not participate to the hypercharge. So these charges does not influence the hypercharge of the particle. And so we have the freedom to choose them to be plus or minus 1 without any consequences on the hypercharge. So we can do this for free, and we can ensure that indeed the HD does not couple to electron and to quark. So that's just one model among others, which can realize this proposal. So that concludes the second part of this talk and the full talk. So let me briefly summarize what we have done here. So we have studied the discrepancy. We have studied the contribution to the discrepancy in the muon G-2, coming from 2 main ingredients. The first one using extra U1 gauge boson and large extra dimensions. And the second one using light stringy states of an Higgs field, of a scalar field. So we have shown that there exist some regions in the parameter space which are compatible with the experimental bounds, which are able to accommodate this discrepancy. So either to contribute to bridge the gap, to fully bridge the gap, or to bridge the gap partially at least. And we have then built the minimal D-brane configurations, which are able to realize this proposal. And we have shown that they require 5 and 4 stacks of brane respectively for these two proposals. So a possible outlook of this work would be to consider a top-down approach. So would be to embed these constructions into a global string theory model. And so this muon G-2 could be very interesting, as it could be used to probe low string scale physics, large extra dimensions, and this intersecting D-brane framework. So thank you very much for your attention.
Thank you. Are there any questions? Okay, I'm not an expert, so maybe it's a bit naive. So I was wondering, like, if you don't use any string theory or branes, how difficult is just like adding some extra particles to fix this discrepancy? Like, it seems naively that you have like many parameters like masses, spins, couplings, and you just need to like fix only a single number.
So your question is, how can we embed this in a string theory construction?
No, like if not just field theory, just adding extra species of particles.
So by construction, the intersecting D-brane models have some extra particles. In all intersecting D-brane models, you always have some extra gauge boson and this kind of stringy states, which are the excitation living in the intersection. So you always, in any intersecting D-brane models, you always have these extra particles. And precisely, we are using these extra particles to see whether or not they can explain the discrepancy. So in some sense, if we live in an intersecting D-brane framework, there should be somewhere some extra particles compared to the standard model ones.
Mm-hmm. And if you just use field theory, let's say no branes, no string theory, so how difficult is to fix this? Just adding...
If I use only field theory, you said?
Yeah, just usual field theory.
Then usual field theory, you are free to consider extra particles, yeah. But it's a bit, it's not very natural. I mean, in field theory, you can add as many particles as you want, but there is no strong motivation. Here, the motivation really comes from the intersecting D-brane physics, which have these ingredients by construction.
Mm-hmm.
In field theory, it's not really, there is not real motivations in string theory to do this.
Okay, but still it's possible, right? So there is probably
it's possible, yes. You can consider in field theory extra U1 gauge boson that you add by hand in your model.
Mm-hmm. Okay, and so you had these small masses, like in small angles. So again, I don't know how usually like the philosophy works, but isn't this like considered to be some sort of fine tuning?
Yes and no, I would say. So this small mass, it is a fine tuning in the sense that we have considered fixed values for the masses and so on. But in any case, we can have small intersection angles which lead to small particles and which should have phenomenological consequences. So the particular value of theta here, we have just fixed it to fix the IDs. But in any case, we can have very light excitations if we have very small intersection angle.
Mm-hmm.
So we say, okay, we have this tower of states. Basically, what's happened phenomenologically if we have some small intersection angle? What are the consequences? What are the observable consequences?
But is there like any natural mechanism which makes D-branes like almost parallel to each other.
So then that's from the string theory point of view, that would be a matter of moduli stabilization. So if you want to have a very, very small angle here, then you can have, for instance, a very large dimension in the internal space. You can build this small angle by different ways. If you consider this size to be very, very large, this size to be very, very small, then you get almost parallel D-brane. And so then this becomes a matter of moduli stabilization. Why do we have such sizes in the compact manifold, in the internal manifold?
Excuse me, may I ask a question?
Yes, sure.
Excuse me, did you try to look some other discrepancies? For instance, W boson mass or B anomalies? And did you include also some collider bounds from Higgs searches, say, in your model?
Not yet, but that could be another possibility.
Because all these things could shrink significantly your parameter spaces.
If you consider other constraints coming from W boson mass and so on.
And in your model, do you have some, say, proper dark matter candidates?
So in the first model, as I said here, in the first model, you can introduce very easily dark matter candidates which satisfy the main bounds of the dark matter masses. So I didn't went to the detail of this, but we have been able to do this in this model because of these two branes which does not participate to the hypercharge.
Thanks.
By the way, do you understand correctly that all these corrections are just one loop results?
Yes, exactly. It's everything everywhere. It's one loop correction.
And the rest is just negligible, right?
The rest is assumed to be negligible.
And what do you do with gravity, or you just ignore it?
Oh, it's ignored. So gravity only plays a role, as I showed here. So we consider a low string scale model. So in order to lower the string scale in this region, we consider large extra dimensions where gravity propagates. So we only we have this large bulk where gravitons can propagate, but we don't include gravitational effects in this model.
Okay, thank you. So any other questions? Okay, since we don't have any further questions, thank you very much. And yeah, to everyone else, see you next time.
Okay, thank you very much for the invitation.
Thank you.
Bye-bye.